Hello everyone, I'm Ning, a first-year PhD student from AMI at the University of Alberta. I'm happy to be here and share our work, Text Editing as Imitation Game, which was done when I was at Alibaba Group in collaboration with Autodesk, UIUC, and SJTU. Text editing is a critical group of processing tasks aiming to change the text by operations such as insertion, deletion, and substitution for a certain need, which can be applied to text simplification, grammar correction, punctuation restoration, and just name a few here. We can take the case on the right side as a simple example where we want to edit 1, 1, 2 into 1 plus 1 equals 2 as a valid equation. The neural sequence-to-sequence framework established itself as the primary approach to text editing by treating the problem as machine translation. Applying a sequence-to-sequence modeling is simple, where the system can simply be built on input-output data without too much processing effort. But even with a copy mechanism, an end-to-end model can struggle to translate overlap part, which is not required to be edited. So sequence tagging is often found more appropriate when there is an overlap. Here, each tag represents a token-level action and it determines operation on its attached token. A model can avoid modifying the overlap by assigning a special keeper tag. As each tag can be treated as the action at token level, we can name sequence tagging as token-level action generation as well. But the action space is limited to token-level modifications, such as deletion or insertion just after that attached token. Some others train the agent to generate actions at the sequence level, and we currently edit the text during the interaction with an environment. Thus, the agent can enjoy the dynamic representation of the intermediate state, and the editing task is now decomposed as a sequence of subtasks to predict one single action for the current state. This allows the highest degrees of flexibility at the sequence level, but imitation learning in sequence-level action generation is less well defined, even though its principle has been followed in the text editing and in many other tasks. Sequence tagging and sequence generation against end-to-end are presented here given the same example. It is noted that both sequence tagging and sequence generation allows imitation learning and recurrent inference. In this work, we propose to format text editing as an imitation game following such MDP definition. State here is a set of text sequences. We can think of a source sequence X as the initial state, and the target sequence Y as the goal state, and all the other text during the editing as the intermediate state. Thus, the path from X to Y can be a set of sequential state. Action is a set of action sequences. For example, the action insert pose 3 equal means insert equal mark at the third position, where insert is the operation token, pose 3 is the position token, and the equal mark is the vocabulary token. The action design depends on the specific added matrix E as long as we can successfully edit X into Y. The transaction matrix P can be omitted here, as we know the edit can always happen due to the nature of the task, and the probability is always 1. The environment of text editing is episodic and allows control of the entire editing process. For example, the environment can refuse to implement invalid action and terminate the game if a maximum number of iterations has been consumed. Since we focus on behavior cloning in imitation learning, the reward function can be omitted here as well. And it turned out to be a simplified MDP defined by the tuple of state, action, and the environment. Here is an example of the imitation game for the same case. The editing can be completed in 3 actions. We first insert the addition mark at the first position, and then insert the equal mark at the third position. The last action with the special mark down means no more actions as needed. Thus, we can return the current state as the final output directly. However, how do we get expert demonstrations for the agent to imitate? To answer this question, we show how to make use of dynamic programming to convert conventional seq-to-seq data into state-to-action one. The basic idea here is to calculate the minimum edit distance between X and Y given the edit matrix. We can get a trajectory by backtracing eventually. Another problem is that imitation learning often suffers from distribution shift, which means an agent's mistake can easily put it into a state that agent has never seen during training. For this issue, we propose trajectory augmentation that augments the expert demonstrations and actively exposes shifted state to the agent. Specifically, we used divided and conquer to drop out actions from expert demonstrations, and thus produce more trajectories that are not covered previously. Let's only use existing expert demonstrations to preserve the IID assumption, and is universally doable without the dependency on the downstream task. It also does not need domain knowledge, labeling work, and further evaluation. We also take advantage of the flexibility at the sequence level to fix action to be of the same length so that we can employ a linear layer after encoder to align the hidden dimension. By that, we introduce a dual decoder structure D2 that not only parallels the decoding but also keeps the interdependencies among action tokens. We evaluate our method on the AE benchmarks, including operator restoration, equation simplification, and equation correction. The data statistics is in Table 1, and we also provide some examples for each task in Table 2. We follow the same dataset settings of the previous work for a fair comparison. To locate our method in the big picture, we have the following models for the experiment. We report previous works as end-to-end, tagging, and recurrence. We noticed that the previous work allowed data augmentation. For a fair comparison, we run the source code to disable the data augmentation as recurrent star. We also reproduce recurrent star in our pipeline as AR, means autoregressive. We further add more encoder layers to get a more powerful AR star. They are the baselines with autoregressive decoders. We simply replace the decoder with linear layer in AR star and get NAR as a non-autoregressive baseline. NAR star is just our method with the proposed D2 structure, and we also specify the use of TA. What stands out in the table is the dominance of NAR star in terms of equation accuracy for all three tasks. As expected, the incorporation of TA consistently promotes the accuracy of all models in our test. Also, it appears that TA is more effective for non-autoregressive models than autoregressive ones. The figure on the left side shows the learning curve, and the figure on the right side presents the inference efficiency. We find NAR star generally need less training to converge, and NAR star saves much time for action generation, and therefore returns the final output faster. As a further step, we find that the same operation actually can be presented as different action sequences, so we simply swap the action token but present the same operation. We find NAR star holds around its result and even slightly improves in the third action design. This means NAR star can still catch the position information for various action token order. We think such robustness allows greater freedom of action design. Additionally, a different edit matrix can produce different expert demonstrations. To analyze trajectory optimization, here we involve a new edit matrix LCS, standing for longest common subsequence. The difference between LCS and the Levenstein is the involvement of a replacement operation. We evaluate our method in AEC but are grouped into two test sets, with or without replacement. We can see that LCS is better when replacement is not used, but Levenstein is better when a replacement operation can help to shorten the trajectory length. This observation supports our assumption that a good edit matrix is important. Finally, we conduct an ablation study to see the contribution of our D2 structure. We have several baselines here. Decoder 0 means we only use the single decoder, and the shared decoders means both decoders in the D2 structure share the same parameter. We can see that among 4 decoders, NAR star dominates all 3 imitation games. When incorporating TA, the gap between NAR star and the others is even more obvious. Since they share the same encoder, we can say that such a gap emphasizes the benefits of D2. So to conclude, we frame text editing into an imitation game formally defined as an MDP, allowing the highest degrees of flexibility to design actions at the sequence level. We involve TG to translate input-output data to state action demonstrations for imitation learning. We introduce D2, a novel non-autoregressive decoder, boosting the learning in terms of accuracy, efficiency, and robustness. Finally, we proposed a corresponding TA technique to mitigate distribution shift problem imitation learning often suffers from. The involvement of a reward function, the optimization of the trajectories, and the design of the sequence-level actions and their applications are interesting for future work. For limitations, we have to call the encoder multiple times to get dynamic state representation, so this can be a potential efficiency problem here. Also, the application of our method in more realistic editing tasks remains a concern. Overall, we believe turning tasks into games that agents feel more comfortable with can benefit future studies in the direction of RL in LP. So that's it. Feel free to take a look at our paper on arXiv and the code released on GitHub. Thanks for your attention. Appreciate it.